Is this good now? Okay. All right. So I'm going to talk about a locomotive truck-based autonomous track geometry measurement system. There are a lot of words. So I think this is a pretty exciting development, and there's some interesting findings that I think you'll hopefully you'll enjoy that. So a couple of slides as an introductory slides, and I'll dive into the details. So first, Holland. If you are in railroad industry, you very likely heard about Holland. It's a brand in the industry since 1935, the largest flash butt welder service provider in the world, more than 200 mobile units. And there are several business units. I represent today the RMSS, Rail Measurement Systems and Services, known as Trackstar, and have been serving the industry since 1995. And born with Trackstar, and then today we offer some Argus technologies and RangeCam software, which has been around for 30 years, one of the first track geometry and rail profile analysis software packages, and Genesis data management platform, which was born around our autonomous inspection platform. And we're in the middle of migrating RangeCam to this web-based platform. So a little bit about our business unit, RMSS, really quick. Again, started in 1995. I don't know if we are the first one, but they're likely one of the first high rail-based GRMS provider back then in 1995. And started with one truck, grew to be 18, and it was an operations-based team. But around 2008, the transition started because we acquired RangeCam technology, and then in 2017 we acquired Vista geometry technology, and then we built the product development team and turned it into an Argus system. So we have today roughly 20 engineers, software developers, hardware designers, QAs, test engineers dedicated to this Argus product portfolio, as well as supporting Trackstar. And then in 2018, we started releasing new products like fully portable hang-on geometry measurement systems deployed from high rails. 2019, we started working on our locomotive-based autonomous system. We made a strategic decision at that time, and I have another timeline about autonomous track geometry measurements. So when you look at the timeline, you look at the market, and we made a decision that, okay, we're going to focus on locomotive. In July 2020, we launched our first pilot program. And after that, we said, well, maybe we can run our hang-on systems autonomously, since track inspectors spend time on track, so they just push the button and let the run system autonomously. So we launched we did a really nice experiment about that. And then we partnered with Cordell from Australia, and we provide now LiDAR and video imagery services. And the latest is this Argus 2.0. We're really excited about that because we literally redesigned the geometry system from scratch using the latest and greatest systems on chips, the latest semiconductor technologies, 10 times more processing power, and giving us a lot of opportunities to do a lot more processing on the device, because we know that that's how where the direction is going. And plus, we redesigned the system, and you can see how complicated it looks. They're like, it's a 14-layer board, and we're able to integrate it seamlessly with other technologies. So a lot of processing power. So, some introductory slides again. I'll go through that quickly. I think pretty much everybody knows the fundamentals of geometry, but for the integrity of presentation, I think it's useful. So the modern geometry systems, they pretty much all of them work the same way. There's some different deviations. If you go to Europe and Japan, I have seen different way of doing it, but mainly you have laser optic systems fused with IMU. So you have lasers illuminating rail. You use a structural illumination. Cameras pick up the laser illumination. You have high processing power on device. You identify top point and gauge point. You have 60-degree of freedom measurement system on your beam. You fuse that information, bunch of filtering, bunch of signal processing, a lot of algorithms. And at the end of the day, what you do, you just map out individually each rails with respect to each other, and as a track in the three-dimensional space. So that's what modern geometry systems do, okay? And so to my knowledge, there are more than 30 different geometry channels. You can even go up to 50, but at the basics, gauge, cross-level, surface alignment, these are the fundamental channels. The rest, you can drive a lot different versions. You can pick different chord lengths. You can get space curve versus chord based. And then, yeah, just based on the needs, we have customers that they have their own unique channels. But everything comes from FRA 213. That's the core. That's the law, and defines the track safety and well-being of track. Defines the track geometry limits. And then we have ARIMA and APTA for standards. ARIMA Chapter 2, the best practices. APTA for transits. As far as everything complies with FRA 213, that's fine. And then on top of that, railroads have their own more stringent rules and applications. So that's pretty much what lays out when it comes to regulations, standards, and best practices in geometry. I copied and pasted one of my favorite slides from Mr. Gary Carr, embracing technology for railroad track inspection. That it's a great presentation, and this is one of my favorite slides. It says the systems that address track defect incidents, and geometry is up there. And when you think about it, it just makes a lot of sense. So in FRA 213, there are requirements for geometry measurements, but it's a lot more than that. It defines the well-being of cross tie and ballast and you know, fastening systems and all of that. But when you have problems with those, that reflects to geometry, not always, but mostly. So if there's a problem with your geometry, that means that there's something wrong with your track or combination of problems. So that's why I think it just makes sense to see geometry up there, that it includes a lot of information about the incidence of the track. And then followed by flaw detections, switch inspection, and on and on. So geometry is a very valuable data. And rail profile, so depending on what configuration you use, we have small footprint geometry systems that measure the geometry from the gauge side, so you cover here and here. But if you put additional sensors on the field side, so you get the complete view, it sounds like only one measurement, but when you map out a rail, if you start counting down vertical wear, gauge face wear, rail head slope, base to height ratio, lip area, total loss area, rail cant, there's so many information is extracted from just that point cloud that come from the rail measurement. Is that it? No, there's more. Again, it's very valuable. This is coming from ARIMA Chapter 2. I think they did a very good job. Well, I'm part of the committee too. So it lays out where and how the track geometry data is used. I think it does a really good job explaining it. Well, first of all, 213 compliance. In addition to that, spot maintenance, operational safety, and then track maintenance and renewal planning. I like all these machine learnings, deep learning applications, but before that, actually, there's some basic stuff defined, like track quality indices. They also give you a lot of value too, and they were all defined in Chapter 2. If you have frequent enough measurements, I guess that makes your job easier and make it more accurate. And when you fix those spots or renew your track or maintain your track, then somebody has to audit that and make sure the work is done properly. And again, you need geometry systems to do that. So it's also used for auditing and quality assurance. Engineering analysis, I know some people here have done a lot of work in derailment investigation modeling, multi-body simulation packages, all these things need geometry data. So it's used in many different analyses. Service and line changes, if you incorporate passengers service in it or hazmat in it, and requirements change. So you need geometry data. And exciting part, sometimes you take enough measurements, you look at your line and you say, wait a second, I can upgrade this line because geometry looks really good. I can comply with one upper class. So geometry data is used for that. And also for claims, when there's an accident, derailment, some people open those files and look at the records. So it's a pretty valuable data per pound. So it doesn't give you the complete picture of full inspection, but in my opinion, the most valuable data within the inspection domain. When we look at the FRA derailment records, there are some graphs that are plotted since 1975. There's a huge improvements. And then you see some years that it just staled and doesn't move down. But within the last 5 years, if you look at it, we can see clearly on the gauge side, for example, mainline gauge mainline derailments are now single digit. And we see a clear a trend there. It seems like on mainline cross level and mainline surface, we are also hanging around low teens or single digits. Alignment is a little bit more, and that's sunking involved, and that's something to do with rail neutral temperature. I think that more work needs to be done in that area. So alignment is a little bit more than cross level and surface. And the other interesting finding was that yards just stand out too much, and there's nothing, everything on that domain is preventable, but it's a separate discussion why I think there are more yard derailments. So, and one good thing about, well, I don't know if you could have called a positive thing, but the geometry related derailments are generally not as wild as broken rail or weld, as you can imagine. So not all derailments are equal from that perspective, but still it's a disruption to your yard, disruption to your service, and a safety issue that we need to address. So, slide. So please take this with a grain of salt. That's my opinion, my limited knowledge in this domain. But and I have seen some papers that laid out the history of autonomous geometry measurement system, but within only the scope of geometry system. I look at it a little differently. So basically, the autonomous geometry measurement goes back to 20 years ago, 2002 image map in UK. And we are privileged to have the gentleman who was part of that program, Mr. Wayne Dudgeon, our principal staff engineer, has been with us for 10 years. It worked out. They deployed it in some units. But back then, there was no 5G, no 4G, no 3G. They didn't have any G. They were basically transmitting data through almost like PTC systems. They installed antennas and they were transmitting data that way on there. So how expensive that is, imagine back 20 years ago. 20 years ago, there were no cloud computing, cloud services, no data scientists. So it was just not the right environment. You can make the software and hardware work autonomously, but it's not the only criteria. You need the environment ready for it. So when you look at that timeline, in 2008, we see the first ATGMS system funded by FRA, built by ENSCO under that Amtrak Auto Train. And then at the same time, you see in 2008, PTC mandate starts. I was working on some PTC projects. Actually, a fun fact that 2009, the first time data scientist job is opened by Facebook. And at that time, I was working on equipment health monitoring systems like trackside detection systems, wheel impact load detectors. So I was dealing with really large data sets, and we were making fun of each other as data scientists, but it turned out to be a real thing. So it seems like I didn't have a good vision back then, and I don't have now too. So But so just the right environment started to shape up around that time frame. I think there are several units built by FI ENSCO in that domain. Generally units with power available, and then they focused on unpowered platforms like Boxcar. I see it was around 2015, I think it was released and tested in the field. BNSF had their own approach to it. They had a passenger coach car converted inspection cars, ran autonomously around 2017. And now in 2020 timeframe, we started hearing the locomotive system. So Norfolk Southern announced their own internal design locomotive system. We launched our own system around July 2020. Kawasaki, Avante, and those are the ones that I know. Please, if there's anything missing, I apologize. But according to my, let's say, review, there should be right around 50 units in North America today, mostly boxcars. And in addition to that, passenger coach cars, locomotive units, and this number is obviously going to grow. And today we have 5G network. It's going to be more and more common, and self-driving cars. And Intel released a custom chip that you can run AI algorithms on the device, which is amazing. Just a couple of weeks ago. So the environment is right. I think the only missing part is the regulation yet. So that's a separate discussion. Why locomotive and why truck mounted? Sorry, I have a hard time to control the position of this microphone. So when we look at that market again around 2019, boxcar UGMS was the main, let's say, product in that domain. And we wanted to provide a better alternative. That was our vision for this product. And we said, okay, we will focus on locomotive. Locomotive has all the power that you need. So that gives you a couple of advantages. So you don't need to spend money on solar panels, power generators, backup batteries, and power management and control systems and all that stuff. So that reduced the cost, and it reduced the number of potential points that can fail. Anything that you throw on an autonomous system at some point will need a replacement or inspection or maintenance. So simpler, the better it is. So that makes the job easier from that perspective. The other thing is you don't need to invest in a dedicated car and associated customization. You upfit it. It's just a revenue service vehicle. You just go and install it. When I said it was easier, well, from that perspective, that makes sense, but it's actually a difficult job to put something on a locomotive truck and run, right? And especially a sophisticated hardware. I have a couple of slides about that. And the other thing is why locomotive, why truck mount? Well, locomotive has 3 36-ton axle load under the same truck frame. From that perspective, it provides the most stringent load environment in revenue service. Generally, they travel more than boxcars, but I don't think it's like significantly, but probably 10-20% more, possibly. And then it depends on the railroad as well. And why truck mount? Because there are a couple of advantages. You can capture the track irregularities and frequencies better than car body level. There's a possibility that some of the frequencies may be dampened out till they go to the car body. So we think that there's a better, a little bit of accuracy improvement there. And then when you mount it to the truck, you can get the maximum rail profile coverage even at the sharpest curve. So when you're on the car body rotates on truck. If you go like 20-degree curve, 6-axle locomotives are spec'd out for 27-degree. If you go 15-degree curve, let's say, it's one of the sharp curves, that there's a huge overhang. It depends on where you are on the car body, but truck always follow the track center line. So that means that you still get the maximum profile coverage when you measure it from the truck. because it doesn't deviate from the track center line. Just a visual representation of it. Not all, I think I said not all derailments are equal, and not all geometry measurements are equal. So you can use the same system, same software, same hardware, put it on a 2-ton high rail versus 200-ton locomotive. You're going to get very different geometry, and you're going to find different defects. So and it's important where you measure it from and where you mount it to. So, or another example, you measure from locomotive, but from coupler, way away from the wheel load environment, then you're going to measure unloaded geometry again. So where you mount and which platform you pick is very important. I think results has to be interpreted based on that fact. There's a great study funded by FRA, conducted by University of Nebraska at Lincoln. I think this was about vertical stiffness measurement technology, if I remember correctly, but it's a great research. So it was on the left side, we see the track deflection when they loaded coal cars. Coal cars have 36-ton axle load, trucks have 2 axles, and you see the deflection, and then when the locomotive comes in, you see the difference. So it's very obvious, and I think on the right side, I don't know if this has, there you go. On the right side here, this represents how the position of the rail changes with respect to the wheel load concentration location. Overall, it's pretty straightforward. Closer you are to the truck center, more stringent measurement that you're taking. And then further away you are from there, it's not a linear change. So closer the better, but you can get to a point that, for example, the excessive case center of the car, you're going to measure the uplift rather than finding that, so mount same exact technology here and here under the same same vehicle, you're going to get very different measurements. Those were examples about vertical loading. Okay, and then lateral is also another area. So when I used to work at TTCI, this was we were working on rolling contact fatigue, and these are the measurements taken from a loaded grain car, 36-ton axle load with an instrumental wheel set, and you can see the lateral and longitudinal forces as a function of degree of curve. I mean, on tangent track, it's not much. I mean, if you ever looked at instrumental wheel set data, you'll even see that on tangent track, sometimes you measure like negative 300 pounds, positive couple hundred pounds. It's really small because of the oscillation behavior of the wheel set. You push in and out, but it's really negligible. But when you go to the curves, the same vehicle can widen the rail as much as 12, 14, 15,000 pounds at 12th degree. Same vehicle. And then again, it's important. Where do you measure? You need to be close to the lead axle as much as possible. And also even the steering properties of your truck will make a difference. And so you have to be cognizant about that. So about our truck mounted track geometry measurement system, there is no standard that we can look up how to design this. So we came up with our own requirements. The challenge was that, okay, we're going to put it in front of the traction motor. There's an electromagnetic interference. We found the most stringent military spec about EMI, electromagnetic interference. We multiplied by 2. We run our system. We re-engineered it, make sure that it's not affected by that. And then we mounted the triaxial accelerometer to the location where we want to mount, ran it for several weeks, look at the acceleration data, shock and vibration information, recreated that in the lab environment, and then design our mount accordingly. Oh, here. So this is the shaker table. There's a 3D printed rail. The gauge distance system is running with a simulated encoder data, and we are looking at our geometry system while shaking at the shock and vibe environment. And we ran these for 2 weeks, and it was a great test. So basically what we did, I think I'm running out of my time. I'll just wrap up really quickly. Basically what we did, let me find this one too. The goal was here that we wanted to keep the frequencies that we need for geometry calculation, okay? But anything else we wanted to eliminate because anything else is not useful for us and it's damaging the hardware. So for geometry calculation, you need relatively low frequencies. So when the truck is going and following the track, you don't want the system damping the energy. So it must move with the track. But anything at higher frequencies, that is like mechanical shocks, that you just need to eliminate that. And that's what we accomplished after several nonlinear simulations and tests. This is the graph, for example. I just masked the numbers, but there's a frequency that we tuned up the orientation of isolators, the thickness, dampening, stiffening, all these features in a way that we only isolate the shocks that we don't need. So that's the, here is the frequency that above that we don't need. And this is the energy dissipation by the isolators that protects the hardware. That's how it has been in operation for 2 years without any maintenance. And that was our test setup, how we generated that data. Well, time flies. I think I'm out of my time. Sorry about that. And this is some pictures from our inspections. One issue we had that we use a mechanical encoder, and we didn't have any protector for it. It was knocked down, and then we built a cage for it and solved the problem. And then we designed this bracket that allows the degree of freedom so that it doesn't snap and break. It works fine now. But we focused on non-contact distance measurement technologies, and we verified the performance of it for low speed. So we'll probably use it on our high rails soon, and we need to test it at the higher speed on the locomotive. So the reason is that one problem with encoders, people who deal with data will understand, you go this way, it measures the 12-degree curve at the low rail, and it comes back, and the encoder is on the high rail. There's a natural distance difference between the two, so you cannot overlay the data. So we will measure the distance at the center line of the track. Okay, one more thing. It's interesting for ties. One thing we observed from the locomotive-based system, we only see that on a tangent track, wood tie, tangent track, especially lower track class, tight gauge. We compare the data with the inspection car, you don't see that. You only see it on geometry, in only locomotive. We think that it's because of that 3 36-ton axle load pressing 1x40 cant rail like this way. And if your ties are not stiff enough, the spots that are not stiff enough, it shows that in the gauge readings. So because it's random. Concrete ties, you don't see that. So we think that that's a pretty valuable information for tie and fastening system performance. That's the only platform you can catch. Typically, you measure most of the channels 20% more than heavy inspection cars with this type of arrangement. Yeah, so some of the field validations, alignments on turnouts, and cross level at a spiral, wide gauge, warp and twist. We definitely need more field validation and more data analytics, and hopefully I'll share some more exciting findings in the near future. So sorry about that, I'm over my time. If you have any questions, please feel free to reach out. Thank you.